All right, Auto 2, we're going to be talking about our last topic of the trimester, which is emission controls. And we're going to be looking at the different systems that are involved in controlling pollution, and we're going to look at different pollutants. And in this picture, which I believe is downtown Los Angeles, you can see the smog, okay? You can see the filthy air kind of trapped on the top and the earth below, and a lot of health concerns from smog. And over the years, for the last 50 years, we've been working on the smog problem in Los Angeles. It's definitely improved. Cars are polluting way, way less than they used to, but it's still an issue, still a concern. So let's talk about it some here. So here's our pollutants. Hydrocarbons, which are a leftover byproduct of combustion of fuel, whether it be gasoline, diesel, and oxygen. Carbon monoxide, which you know is colorless, odorless, tasteless, and lethal. That is, it will kill you. Carbon dioxide, which is also not good for you necessarily, but in the combustion process, we want to produce maximum carbon dioxide so that we're producing this. If we want to talk about this as a greenhouse gas and talk about ridding ourselves of that, we've got to talk about not burning fossil fuels, at least at this time. It's our only solution. Oxides of nitrogen, definite pollutant, definitely part of that visual component of smog. Oxygen is a non-pollutant, but it is a slight byproduct of combustion, although we want to consume as much as possible. We get nitrogen and water, and these are not pollutants as well. So let's continue here. Those are our pollutants, or at least our gases, and some non-pollutants. Smog, visible smog, comes from the word smoke and fog, and it's harmful to living things, but it is oxides of nitrogen and particulates in the presence of sunlight. So when it says pollutants combined with oxygen and nitrogen in the presence of sunlight, this is what we call photochemical smog. Okay, so that's our visible airborne pollution. So this little gauge, or this little picture, shows air-fuel ratio and pollution. In other words, pollution as a byproduct of air-fuel ratio. So if this direction is richer, more fuel, less air, and this is leaner, more air, less fuel, what happens with pollution? Well, as we go richer, hydrocarbons and carbon monoxide pollution goes up and NOx goes down. As we go leaner, oxides of nitrogen goes up and hydrocarbons and carbon monoxide goes down. So around 14.7:1, or these days we just say 15:1 air-fuel ratio at sea level, is what we consider to be our chemically correct or ideal air-fuel ratio. So the problem we have is that if we run leaner to get better gas mileage, the engine runs hotter and some pollution goes down, but some goes up. If we go richer, we get more power, less gas mileage, but certain pollution goes up and some goes down. And all three of these, hydrocarbons, carbon monoxide, and oxides of nitrogen, are what I call real pollution, meaning undeniable health, undeniably hurts our health, undeniably, without argument, is bad for the environment, and so on. So where does the pollution come from in a car? Well, of the total pie of pollution, 60% of our emissions comes out of the exhaust, in the form of unburned hydrocarbons, carbon monoxide, oxides of nitrogen. About 20% of our emissions are from crankcase vapors, meaning vapors that go past the rings. We call them blow-by vapors. And about 20% are from fuel evaporization. So you can see, obviously, the main sources here, and this is where we've put so much effort, but we have also been able to take care of most all of this. This has been the area, a little bit more modern area, that we've been dealing with. Although we started dealing with it in 1966, we've gotten more aggressive with that one in late. But anyways, here's our source of vehicle pollution. By the way, one thing that's not being talked about here, this is consumer use pollution, meaning as you drive the car, this is what happens, okay? We're not talking about production pollution, and we're not talking about post-production pollution, meaning when you send the car to the scrapyard or it gets recycled, etc. We have pollution in both of those cases. This is just the pollution that's made as you use the car, just FYI. So here's the pollutants again produced out of an engine: hydrocarbons, carbon monoxide, oxides of nitrogen, and we do get particulates, especially with diesel. Older diesels, we get particulates, which is like soot and so on. But these are our exhaust emissions, so we'll talk about these. Hydrocarbons. First, essentially hydrocarbons are unburned fuel. In the automotive field, we say that hydrocarbon pollution is a byproduct of inefficient combustion. It's the way we have to talk about it. We don't really talk about it as raw gasoline. We really talk about it as combustion efficiency. Now, the chemist would talk about it as raw fuel, HC, but we talk about it as combustion efficiency. We're burning petroleum products unless we have, a full electric car, and this pollution, this hydrocarbon is produced by incomplete combustion or fuel evaporation. So we want to try and thoroughly burn all of our air and fuel to get rid of hydrocarbons. Carbon monoxide, again, is a byproduct of incomplete combustion. Remember, it's toxic, it's deadly to you. You can't taste it or see it or smell it. And you can see its health effects. And it's caused by a rich air-fuel mixture. So we say that CO is our rich, lean indicator. If CO is high, we're rich. If CO is low, we're lean. So when we're tuning a car, at least we used to, and back in the day when we had things to tune, air-fuel ratio, ignition timing, etc., we would look at CO on an exhaust gas analyzer to kind of decide where we were. It's still a very helpful device these days, although in the scan tool live data, we can look at other things like what we call short-term and long-term fuel trim and kind of know where we are in terms of air-fuel ratio, etc. But anyways, that's carbon monoxide. Next is oxides of nitrogen, and it says air consists of 79% nitrogen, 21% oxygen. We're about 20.7% oxygen here at San Luis High based on our sea level. We're about 140 feet above sea level, and that's what my exhaust gas analyzer tells me. Above 2,500 degrees, nitrogen and oxygen form in a polluting compound. Now, the reason why they call it NOx, that's a variable because it'll exist as NO1, NO2, NO3, NO4, etc., etc. So the causes of oxides of nitrogen are high compression ratio, lean mixture, and high operating temperatures. Anything that makes the combustion chamber hot is going to produce not oxides of nitrogen. Therefore, one of the goals we have with certain emission control devices is to keep the combustion chamber temperature below 2,500 degrees, but as close to it as we can so we don't produce oxides of nitrogen. Particulates, carbon soot, fuel additives. Historically, there's been a problem with diesels, although they've gotten a lot cleaner. A rich air-fuel mixture or some kind of mechanical problem will be a cause of this. It says 30% settle out of the air quickly and 70% float for extended period of time. A city like Phoenix has a real trouble with particulates because the environment down in Phoenix is so dusty. And it contributes to the pollution, though it's a naturally occurring thing. It's just the dust from the desert. So next, we want to talk about a whole list of emission control devices. And if you look at this, you don't need to write anything down yet because we're going to talk about each of them individually on the ensuing slides. But you got 1, 2, 3, 4, 5, 6, 7 emission control devices. Of these 7, you will see. So, sorry, I got interrupted there. We're going to look at all these different systems and talk about them. This one's not really around anymore, and this one's not around anymore, but these 1, 2, 3, 4, 5 definitely are. Let's keep going. Okay, so posit crankcase ventilation. So starting in 1965, in order to reduce hydrocarbons and carbon monoxide that would leak by the rings during combustion. So you have a piston here, and you get combustion going by the rings, and it'll get down into the crankcase. The crankcase is that area housed by the oil pan on the bottom and the block on the top where the crankshaft is. And those vapors had to be removed from the crankcase. Otherwise, they literally pressurize the crankcase and blow the oil pan off. I've actually seen that happen. So what we do in a posit crankcase ventilation is we would suck these vapors out through a PCV hose and a little valve called a PCV valve. and those vapors would be drawn back into the intake manifold and burned in the combustion chamber. So that's how we've dealt with them. A PCV system is on every car, foreign, domestic, since the 60s, and they're still around and they still will be around. So that's a positive crankcase ventilation system. I'll show you a valve in just a moment here. So it says PCV controls flow through the system. It's located in the valve cover intake manifold or side of the block, and it varies flow for idle, cruise, acceleration. It prevents reverse flow, so it's one way or a positive valve. And while you're looking at that, I'll grab one to show you here. And so here you go. Here is a PCV valve right here. So this is a PCV valve. This little guy fits into the valve cover, has a little valve that you can shake here that's loose, and you want it to be loose. Intake manifold vacuum goes here, and at idle, when the manifold vacuum's high, it almost sucks it closed actually. At wide open throttle, where vacuum is low, then maximum flow through this happens, and that's when you make lots of crankcase vapors. That's a PCV valve. Let's keep going. Trying to make it go. Computer to there we go. So this is just showing a PCV valve. Here when we have high intake manifold vacuum, it pulls it up against a spring and almost seals it off. At low intake manifold vacuum, let's see, am I looking at this right? Yeah, the spring's going to push it over and it lets a lot of vapors through. And then if we get a backfire on the engine, it pushes it back and seals it off so we don't blow up the crankcase. Okay. Second emission control device is evaporative emission. So in the late 1960s, we introduced evap emissions. And basically, what this is trying to do is take care of those evaporating fuel vapors of hydrocarbons and carbon monoxide that we're getting into the atmosphere. So when a car sits in the sun, as it heats up, the fuel tank puts out a lot of vapors. And those vapors can end up getting into the environment. So we would take those vapors and store them in what's called a charcoal canister, something like this. This was from a Toyota. And this has an activated charcoal that absorbs the fuel vapor. And then at certain times we purge it out. Now, our system's gotten way more complicated. We're not just purging it out anymore. We also have an evap monitor to actually test the system. We seal the system and we either run a vacuum on it, some manufacturers, or we pressurize it, other manufacturers, to make sure the system isn't leaking. If it's leaking, we turn on the check engine light, you get a P0455 or P0456 or something like that that says that you have a small or a large leak. Okay. So here's a tank where fuel vapors, if the car's heat soaking, I mean it's in the sun and it's getting really hot, fuel vapors are going to start evaporating, and we're going to vent those vapors into this activated charcoal canister. And then at certain driving conditions, which will be fully warmed up in closed loop, part throttle cruise, the computer is going to command these vapors to be purged back into the intake manifold, back into the combustion chamber. Okay. So that's the charcoal canister, just showing activated charcoal and how the vapors come in and then they get purged out. So you don't need to write all this down. Just let this go. No notes here, okay? So the fuel tank vapors absorbed by the activated charcoal. A purge solenoid or valve opens when it's the correct time, fully warmed up in closed loop, part throttle cruise. Fresh air is drawn into the canister so we don't put a vacuum on the canister, so we don't, create a vacuum. And incoming air carries the gases to the intake manifold for burning. All right. Again, don't write this down. You don't need to. A purge valve is just a valve that's going to control the flow. It's gotten much simpler with computer controls because now that we have just a little solenoid, a little electric solenoid that we energize, and then we just purge the vapors. It's not real complicated. Okay. What is complicated is the OBD2 monitor that's run to make sure that the system is working. And so this is just showing a purge solenoid, where an electric solenoid is going to be energized and purge into the intake manifold. Okay. So our third system is EGR. EGR is exhaust gas recirculation. EGR's whole goal is to try and reduce combustion chamber temperature to reduce NOx. We want to try and keep combustion chamber temperature below 2,500 degrees Fahrenheit. So it allows burned exhaust gases to enter the intake manifold. Now, a burned exhaust gas is known as an inert gas. It means it's a gas that has no heating or burning potential. Though it may go in there at 700-800 degrees, fairly hot, we don't look at its temperature as important because that's relatively cold compared to 2,500 degrees. So it's an inert gas that doesn't produce any heat. So by pumping exhaust gas back into the combustion chamber, we're taking up some of the volume, we're taking away the potential for fresh air to be in there, and that tends to reduce the temperature of the engine. Does it sound inefficient? Does it sound like it would hurt power? Yes, it does, and it does hurt power a little bit. And it was introduced in 1974. The early systems did not work very well. Cars ran pretty lousy with EGR, but modern cars work much, much better with it. Just one sec. So here's an EGR valve right here. And this was an early system. This was under a 2-barrel carburetor. Carburetor sat right there. And then what would happen is intake manifold vacuum would suck vapors from the exhaust. Now you say, how did the exhaust get in there? Well, they did it several ways. On this one, I'm trying to see if I can see how the exhaust got in there. Okay, so the exhaust got in here into this cavity here through a passage in the intake manifold, went up to the valve. When the valve is commanded open, it goes in here and goes down into the combustion chamber. So we had a vacuum operated EGR valve. Then in later times, and this is what modern cars have today, we have digital EGR, digital electric EGR, and this one has one valve here that gets pulled open by electric solenoid. And then in really modern cars, brand new cars, cars that are 10 years old and newer, we're starting to see EGR go away a little bit with direct injected cars that have variable valve timing, because we have figured out that when we direct inject gasoline into the combustion chamber, it actually has a cooling effect because the fuel is cold, and that tends to bring the temperature down. And if we have variable valve timing, we're starting to open the intake valve earlier and keep the exhaust valve open later, and we get fresh air coming in and mixing. We get exhaust being left in the combustion chamber with the incoming air, and that provides an EGR, what we call an EGR effect. This just shows an EGR valve with a vacuum signal pulling the valve up and letting exhaust gases go through and then into the combustion chamber. So this is at idle. This is at idle this is what we call a ported vacuum signal. There's no vacuum here, so this is closed because we don't want EGR to go into the engine idle because the car wouldn't run idle right. Here we are off idle, fully warmed up, cruising, and the throttle plate's open. We have a vacuum signal now that pulls the diaphragm up, and now exhaust can go in to the intake manifold. This is an electronic EGR valve. These yellow dots here are a copper coil like this. And if we put a plunger and we don't center it between the coil, when we put current through there and it makes a magnet, it'll center the plunger and lift the needle. Okay, so that's just a regular solenoid like a fuel injector or other electric solenoids. And there's showing one that actually has 3 little valves, and that General Motors digital EGR valve can actually open one of those little valves at a time, or all 3 of them. All right, let's keep going. So next is air injection. So this force system forces fresh air into the exhaust ports, or old cars into the catalytic converter to help further oxidize HC and CO. So if we add oxygen, we can actually burn them. So we're actually having burning going on in the exhaust manifold or in the catalytic converter. We're going to cause exhaust gas to continue to burn, like it says. We're going to reduce HC and CO, and it was introduced in 1968. So air injection systems used to, in the 70s, were on everything, and they were a pain because We had to have tubes like this that went into the exhaust manifold, and everybody hated it because it was just a lot more plumbing underneath the hood. It did hurt power because what it did was it tended to superheat the engine because you were putting more air into the exhaust and getting more heat from burning. Modern cars have a little electric smog pump like this, and this thing will pump fresh air into the exhaust manifold, but only during cold start for the first couple of minutes, and then it shuts off, and that's it. So all it's trying to do now is, while the engine's warming up and we're in open loop and we have a rich air-fuel mixture, we're just trying to give some oxygen to the exhaust coming out of the combustion chamber to hopefully burn some of that unburned hydrocarbons and carbon monoxide in the exhaust manifold. So some systems, this is old school systems, you don't really need to write this down because these are old systems. We had a belt-driven pump, we had some piping, and we had check valves so that we didn't get exhaust going backwards, etc. Now we typically have electric pumps, and it's not on every car, it's only on some cars. And again, you don't have to write this down. We had a diverter valve that on older cars would switch the exhaust down to the cat or to the exhaust manifold, or it would just shut the system off. Because if we have a feedback system with an oxygen sensor, we can't put the air into the exhaust manifold during closed loop above the O2 sensor, because the O2 sensor would think, hey, I'm lean, there's all this air, and it would command the computer to make a rich air-fuel mixture, which would be wrong. So when the car went in, so what these systems would do is they'd pump air into the exhaust manifold during open loop, and as soon as the car switched to closed loop, it would start dumping to the catalytic converter. Now that was, early, that was 80s stuff. In the 70s, before computers, we just dumped it in the exhaust manifold all the time because we didn't have O2 sensors. In the new millennium, we're only doing it now upstream in the exhaust manifold and only during open loop, so just for the first couple of minutes of running. So a car that has this, and not many cars have this anymore, but modern Mustangs have it, Suburbans and Tahoes and Yukons tend to have it with certain engine combination, and you'll hear this like sort of high-pitched whirring sound if you cold start, and you'll hear it for like a minute or two, and then it shuts off, and you're wondering what it was. And don't confuse that with the fan clutch on those. Some of those cars have belt-driven fans and fan clutches, and they'll start up, and the clutch will be engaged, and after a moment, the thermostatic spring cools down, disengages the fan clutch, and it gets quiet. So I just don't want you to confuse the two noises. So here's an air injection system, old school, the belt-driven smog pump or air pump, and it would take air and it would pump it into the exhaust manifold over here, the exhaust manifold over here, and try and treat some of that unburned hydrocarbons and carbon monoxide. This is showing a very old car, again, 6-cylinder Chevrolet or Ford with a smog pump pumping air through a diverter valve into this manifold, and each cylinder would get some fresh air. No, that wasn't a 5-cylinder. There's another tube over there. It was a 6-cylinder. So again, you don't need to write anything down here. There were some systems in the 70s that used what they call a pulse air system. It didn't use a pump. It just used exhaust pulses to create a vacuum and suck the vapor of the exhaust into the intake manifold. I'm not going to waste any time showing you parts, even though I have some parts here, because you won't see this. This was only on certain Asian cars in the 70s, and it's just showing how that all works. So I'm going to flip through there. Let's pause here for a moment, get a drink of water. So our next system is the thermostatic air cleaner that was introduced in the 1960s, and you don't need to jot anything down here. And the reason why I say that is because this hasn't been used for 25 years at least. One of the reasons to be aware of it is we're still smogging cars that are 1976 and newer, and so on a smog check, we still have cars that have thermostatic air cleaners. It was introduced in the 60s to help reduce hydrocarbons and carbon monoxide. Its whole goal was to help speed engine warm up by warming the incoming air. So we wanted to warm up the incoming air that was going to go down into a carburetor back then. This would help reduce engine wear because we're not running cold where things aren't expanded as long. This would reduce fuel consumption because we would get off a rich air fuel mixture quicker, and this would reduce hydrocarbon carbon monoxide emissions. So you pretty much only saw it on either carburetor or throttle body engines. And what it looked like was, here's an air cleaner assembly that had an air filter in it. Yes, this one's damaged. And what it had a what we call a heat stove pipe. So there was a flexible pipe that went down to the exhaust manifold. It didn't take exhaust up into here, but just warm air from around the exhaust manifold would go up into here. And what would happen is this thing had a thermostatic switch, and when it got hot, this diaphragm vacuum would pull this diaphragm closed so no more hot air can come up, and they would start taking fresh air from outside. So we like cold air for power, but we like warm air for gas mileage and emissions. So kind of best of both worlds, or trying to get best of both worlds. And as you understand, I think that the dance between engine wear and fuel consumption, exhaust emissions, and power really is a big compromise. If I want more power, I go richer and colder, and I tend to pollute more and get worse gas mileage. If I want better gas mileage, I go leaner. If I go leaner and hotter, I get better gas mileage, but less power, and some pollutions are lower and some are higher. Again, you don't need to write this down. So there was some sort of a vacuum valve and a vacuum motor and a heat control door, and that's everything I was showing you here, all of these components inside here in this vacuum door right here. I think I'm going to sneeze. So they're showing a pretty good picture of the air cleaner assembly with a snorkel. Excuse me. Whew. Spreading coronavirus everywhere. Awesome. Anyways, and so this heat stove or heat shield was just around the exhaust manifold, so it would take warm air from around it up through here, and warm air would go, wow, 200 miles per hour, spreading COVID. All right. And warm air would go into the engine, help warm it up, okay? So this just shows the door closed off to cold air when we're warming up, letting hot air in. And this one was showing when it was warmed up, it would push this seal off the hot air and cold air would come in. And that's it. Now, catalytic converter. Definitely need to talk about a catalytic converter. Every car has a catalytic converter. Most every car has at least 2. Some cars have 4 now. We have lots of catalytic converters. Why? Because they work. And we brought them in 1974 to address, and this one's definitely addressing a vast majority of that 60% of tailpipe emissions. We want to oxidize hydrocarbons and CO down in the cat. We want to convert them to CO2 and H2O. The catalyst is a substance, which was platinum, palladium, and rhodium, that helps make a chemical change or a chemical process to go. So we have 2 processes in a catalytic converter. We have a reduction reaction and we have an oxidation reaction. It says NOx may be converted into nitrogen oxygen. So the first thing we do in a modern is we strip oxygen off nitrogen. That's our reduction. Then in the back part, we combine that oxygen with hydrocarbons and carbon monoxide to try and get H2O and CO2 out of the exhaust. Let me grab one here. So here we are after a little water break. We are back, and what we've got is a bunch of catalytic converters down here on the ground, and I'm going to show them to you. So let me grab the camera and put it down here. So first, here is a catalytic converter that has seen better days. You can see the substrate in there is all broken out. That's why this one got replaced, and it was pretty damaged. But it has this honeycomb substrate that has the catalyst in it. I'm going to show you a brand new one here on the floor. I'll bring up this brand new one here. Is an exhaust manifold and a catalytic converter all in one with an oxygen sensor. If you look inside there, let me get the light so you can kind of see it. Yeah, you can see the little honeycomb substrate down in there, and those little microducts are where the exhaust comes through and gets converted. Here's another one that broke apart. You can see that guy's floating around in there, and that one has definitely seen better days. And then, oh my word, Toyota RAV4, what were you thinking when you made this thing? 4-cylinder engine with 2 catalytic converters. These stinkers are $800 to replace. I replaced that for a friend. Sorry, was it 800 or was it? Gosh, I think it was closer to 1,200. Crazy. What were you thinking, Toyota? Anyway, so this is showing a catalytic converter. You got hydrocarbons, carbon monoxide being converted hopefully to CO2 and H2O. Okay, so just pause for a second. So catalytic converters are on everything. Super important. It's just a couple of thoughts on catalytic converters. It's actually illegal to install a used one in California. You have to put a brand new one on. If I'm a licensed smog check and repair technician in California, if I'm going to replace one, I have to make sure that it fails minimum of two tests for the Bureau of Automotive Repair to say that I'm legally replacing a catalytic converter and charging a customer, etc. Anyways, let's keep going. You don't need to write anything down about early fuel evaporation because early fuel evaporation does not exist anymore on cars. But I want to just share with you what it was. It was several things, but basically what it was a way of trying to heat up the air and fuel going into the engine to get it to atomize better. So we called it early fuel evaporation. This was a little, this is broken out of here, but this had a little honeycomb substrate. This sat underneath a 1-barrel carburetor, and actually went like this. The air and fuel came down in here. We put a 12-volt, this is a 12-volt heater element, and the air and fuel just hit that hot metal and it would tend to atomize it. Does it sound inefficient? You betcha it was. Here's one on a Chevrolet. What this one did was one exhaust manifold would come down and the pipe would go to this. And what we did when the car was cold, we closed this valve. So exhaust went back up and there was a port through a cylinder head that went up underneath the intake manifold and out the other exhaust manifold. So we were routing exhaust gases through a cylinder head, and I was looking to see if I had one over there that I could show you, out the other side. A lot of problems with these, but the attempt was to heat up the incoming air and fuel so it was atomized so that we would get less pollution. Let's keep going. So now we're going to switch gears and talk a little bit of what we call 5-gas analysis. Just going to talk about the different gases and how we measure them and what they indicate to us. So we say that hydrocarbons, the more hydrocarbons, which we measure in parts per million coming out the tailpipe, indicates incomplete combustion. So if we're too lean, meaning not enough fuel, more air, it goes up. If we're too rich, which is not enough air, too much fuel, it goes up. So HC is low in a happy medium of about 15:1. Advancing the timing too much elevates hydrocarbons as well. A vacuum leak or a misfire sends it off the map. A misfire just skyrockets hydrocarbons. All vehicles must be under 100 parts per million except some very older 70s vehicles when we get a smog check. So if I get a misfire, this thing will go to 2,000 or 3,000 parts per million. So all cars have to be under 100 parts per million. And these days, it's pretty easy for us to get a car like that. A good running car today with a good catalytic converter will run like 10 parts per million. I've even seen 5. Let's pause here for my interrupting phone. So next is carbon monoxide. So CO, or carbon monoxide, we call it our rich lean indicator. So when we're rich, it's high. When it's lean, it's low. Again, we call it our rich lean indicator. And it should always be below 1%. And just some simple notes, and I would jot these things down. But when we're looking at the exhaust gas analyzer and we're looking at hydrocarbons, we're thinking, okay, we got a misfire or something's not adjusted right. When we look at CO, we're thinking it's rich or it's lean, and that's what it is. So we got to be below 1% out the tailpipe at all times. Next is oxides of nitrogen, and this is caused by anything that raises the combustion chamber temperature above 2,500 degrees Fahrenheit. So lean mixture, advanced timing, overheating, anything that will cause the combustion chamber to go over that 2,500 degrees is going to be a cause of oxides of nitrogen. It's going to closely mirror hydrocarbons in terms of being too high or too low, and they measure it in grams per mile. Okay, and so when we say we have a 5-gas analyzer, it includes NOx. If we say we have a 4-gas analyzer, it doesn't include NOx. Next is oxygen, and oxygen is excessive. When oxygen is excessive, it indicates a lean condition, so we have too much air, not enough fuel, or we have exhaust dilution. We've got a bunch of holes in the exhaust pipe, and it'll fail it for that reason. So oxygen just kind of gives us an indication of other things, even though it's not a pollutant. It can be as high as 6% with an air injection system functioning, but ideally it's around, in all modern cars, it's going to be somewhere between 0 and 1%. We really want to be 0, because that means we're using the oxygen to oxidize hydrocarbons and carbon monoxide. It confirms what the CO tells us, meaning if the CO is low, really low, that means we're lean, and oxygen will typically be higher, so they mirror each other indirectly, but they both can be reasonable rich lean indicators. It's not such a good, neither of them are really good rich lean indicators behind the catalytic converter if the catalytic converter is working. But in front of the catalytic converter, they will really tell us what the engine's doing in terms of rich and lean. Next is carbon dioxide, and we call this our combustion efficiency indicator. More is better. We want it to be as high, I've seen as high as 16%, preferably between 12 and 16, but more is always better, because that means we're oxidizing carbon monoxide, right? It must be more than the sum of CO and O2, otherwise the machine assumes you got sample dilution caused by holes in the exhaust pipe or the muffler. So CO, if CO is like on some cars was like 2% and O2 was like 7%, which equaled 9%, and the CO2 was 8%, it would fail because it would assume you have exhaust dilution. Okay. A little bit on smog check testing. Let me pause for 1 sec. So I would take some notes on this. So first, whenever you get a smog check, there's always a visual test. This means that all systems must be present and hooked up. They may not be functioning internally, but they have to look like they're functioning. Okay, that's the visual test. The technician or the smog inspector has to make sure the malfunction indicator lamp is off. The MIL, or the check engine light or malfunction indicator lamp, on indicates an emissions failure is present. A MIL flashing indicates potential catalytic converter damage, and I think you remember that from when we did the Auto 1 dash warning icons. Required systems are found on an emission sticker under the hood. So this sticker says right here, EGR, AIR, and catalyst. That's exhaust gas recirculation, air injection reaction, that's the smog pump, and then catalyst is catalytic converter. Okay, so that tells some of the systems there. So we have to get some sort of accurate information to know what equipment should be on the car. It must be present and functioning, otherwise it fails. That's the visual test. So next is a functional test. Now, this is only on certain vintage cars. So before 1996, we would have to do a functional test where we check the timing, and it had to be within plus or minus 2 degrees. And if it didn't, it failed. We had to make sure they had a fuel restrictor in the fuel filler neck. So we had a little pipe to make sure, because regular gas nozzles were larger than the unleaded ones, and so it had to be sure that it wouldn't fit a regular gas nozzle. The gas cap had to be vacuum tested to make sure that it was sealing, and EGR system had to be properly tested. Now notice, as of 9/1/12, 2000 newer needs no EGR functional test, and we've actually gotten rid of even gas cap testing in later models. But before 96, all of these cars had to do it. In other words, if the car is before 1996 in terms of its make, it had to have all of these. Okay. And then the OBD2 system monitors must be complete. No more than 2 monitors can be incomplete before 2005 and 1 after 2005. This has changed. Now it's back to 2001, so I need to edit this. 2 can be incomplete before 2001, and the only one after 2001 is EVAP. Everything else has to be set, but EVAP does not, because sometimes it's very, very difficult to get EVAP monitor to run. Then we would do a tailpipe test, and again, this is before 1996. In the basic area, we would have a static test at idle, and at 2500, we'd check for these gases, okay? This was a 4-gas test, not a 5-gas test. In an enhanced area like LA and Fresno, we have to perform this dynamically on a dynamometer, and we're going to do it at, I think it's at at 15 miles per hour and at 25 miles per hour, and we check for 5 gases. Okay, so this is pre-1996. Everything 96 and newer is called an OIS test, or OBD2 inspection system, and we don't have to do any of this stuff. Okay, but this is still on 76 to 95 cars. So vehicles are tested 1976 and newer. Testing is performed biennially, that is every 2 years in California. So 1976 and newer. Vehicles, this just changed. Vehicles, I believe it's 10 years old and newer are exempt from biennial inspection, and I just renewed my smog repair license, and I think it's 10 years, but I've got to double check. Vehicles 4 years, and I think it's 5 years now. 5 years and newer are exempt from testing at change of ownership. So you don't have to get biennial inspection until like 10 years, I believe, and then 5 years, I believe, and I need to update that. All vehicles 76 and newer must be smogged when they're brought into California. Okay, so when you come into California, 76 and newer, you might have to be smogged. I'm going to give you a website for this, smogcheck.ca.gov, and it talks about licensing requirements and so on. And the Bureau of Automotive Repair does all the licensing and technician certification. I just last week finished my smog update class and so on, and probably should have edited this before we did this PowerPoint, but anyways. For this, 2 years experience, high school counts as 1 year of smog check experience to get your license. You have to pass ASE tests, certain tests, and L1 for an enhanced license. And you have to pass an 80-hour Bureau of Automotive Repair course as well. And again, some of these things change year to year, so but basically this is what you have to do in order to get licensed. The Bureau of Automotive Repair is very serious about technicians being licensed properly, being honest, and doing the smog check properly. They want the air to be clean. There's lots of fines if you break any of the smog laws, and it's a very lucrative business if you do it honestly and correct. Okay, and then you got to pass the smog test too. Okay, so that's it. That's our overview of smog check, or smog systems, pollutants, gases, and the smog check system.